So on the slides, in the last slide, there's a link to the Google Colab.
Okay. Slides and links are not. Okay.
All right. So everybody on the same page?
No.
No.
Sorry, but I'm not. I shouldn't be holding this up. So just go ahead.
Fair enough.
I'm not supposed to talk or ask questions.
Oh, that's right. Yeah.
But you know.
Silencio, Jessica.
Yeah. Sorry.
No worries. All right. So, a couple things that Robert's telling us to do. We have to set the dendrite length to 100 microns. We want to add a species called IP3. It's going to have a diffusion constant of a micron squared per millisecond at t equals 0. And there's going to be a millimole of IP3 in the center of this dendrite. So, and then there's going to be none anywhere else. So, does somebody want to tell me how we can do these first few tasks, at least set the dendrite length?
Is it den dot capital L equals 100 times UM?
Yeah. Did he use my? Okay, no, he didn't. Awesome. All right, great. And then how are we gonna? Actually, I'm sorry. I'm just gonna have to close this door because I can hear myself on the other computer. Okay, so we have to add the species. But before we add the species, does anybody know? Well, he gives us this hint. Before we can add the species, you have to have this corresponding region. So what's the region that we want to specify here? We're only concerned with inside the cell.
Let's go with the dendrite region.
Sure. So this is all arbitrary, right? What we call these things, but it's called. Well, for the sake of names, we'll call it dendar for dendrite region. So that's going to be RxD.region. And does anybody know how we specify the sections that this is in? There's a function in Neuron that lets us sort of do this, quick and easy. Excuse me, sorry.
Is it whole tree?
Sorry?
Whole tree?
So that I think works, but there's an easier way. Does anybody know how you would loop through all the sections that you've defined?
I think it's h.secall, something along that line.
Yeah, all sec. So, and then for neuron region, I don't know if Robert covered this in sufficient detail, but does anybody know what you call the neuron region when we're talking about inside the cell?
I.
Yeah, hi, thanks. And we just have to, so we're not really concerned about geometry here. All we need is the name. And we'll call it.
Sorry, what was that? A something?
Sorry, the A?
Yeah. The I.
Oh, the I. So the I just refers to the. So you might remember if you wanted to record like intracellular something, like intracellular potassium, it would be Ki. And if we wanted to record extracellular potassium, it would be Ko. So this is just I for intracellular or inside.
Intracellular everything, right?
Yeah. Well, okay. So you're right, for the region. So this is saying inside these sections.
Okay, thanks.
Sure. All right, so we got our region, and now we need to make a species. So Does anybody know the syntax for doing that? Just given as a hint. I forgot about this autocomplete thing. So what are the regions that we want this to be in?
Oh wait, sorry. Is this code available somewhere?
Oh yeah. So it's on the last slide. It's on the Google Drives.
In the chat of this, there's a link to the slides. Or I think somebody also put a link directly to this notebook.
Oh yeah. So Marco.
In the chat of this
Oh, okay.
Google Meet.
Thanks.
So yeah, does anybody know how we can specify the region? We want it to be in Dendar, right?
Is it just Dendar?
Well, yeah, but so we actually have to put it in a list because sometimes you might end up having a species that's in multiple regions. So we need the diffusion constant, right? Which he gives us as 1 square micron per millisecond. I'm pretty sure that IP3 doesn't have a charge, so that's not important. We have to name it, right? So we'll just name it IP3. And actually, so this is the tricky part. We need to set the initial value to be 1 millimole between 40 and 60 microns, so like the middle of the dendrite, and 0 elsewhere. And what we can use is a function to do that. So does anybody know how we can write a function to set this? I think Robert mentioned nodes during the lecture, right?
Is this where you have to find the distance between the middle of the segment?
Can
Or
you
like the
speak
middle
up?
of the section?
Sorry.
Is this where you need to find the distance between the node and the middle of the section?
Yeah, well, so actually, I don't think we need to we don't need to really compute the distance. I think it's given to us since it's all in the same section. But it's the right idea, so we're gonna define. What the fuck? Why can't I type? This is so okay. Let me try and reload this. We're gonna lose everything, of course. Oh my god.
You might need to make a copy of the collab file.
Oh, yeah. Let's give that a shot. Share this tab instead. Jesus Christ. Let me try and stop sharing, and I'll try again.
Do you want me to share my screen and I can run through while you talk, Craig?
Yeah, sure. That works. Because yeah, for some reason I can't execute anything on Colab right now. Weird. This isn't the right one. We want the diffusion example, if you could. Oh man, all my
Sorry, which one are we on, Craig?
all my key bindings are wonky. The diffusion example. I think it's
Diffusion
the first,
example.
the top
Okay.
one. Up.
All right. Is that good?
Yeah, great. Thanks.
Okay.
Okay, so just to go back through what we've already done, you can make a region called Dendar.
Okay, so what are we doing now?
I'll type out what we've done before in the chat. So.
Putting this in the chat.
And
there we go. Okay.
species. Oh well, actually, so before we do that, we want to make a function.
Okay.
So we'll call it myinit. Oh, and I'm sorry. Actually, you can use the node dot or the eight. Well, at least Robert suggests using the h dot distance. So, all right. So somebody had suggested that we want to compute the distance. Well, actually, for Christ's sake, it's impossible to see what you're typing.
Oh, I can zoom in here more too.
No, that's fine. I can actually see it now. So yeah, if you want to do like a def myinit, and then anybody know what we want to pass that function as an argument?
Sorry, can you repeat the question? I was...
So what do we want to pass myinit as an argument?
Okay. Self, right?
Or I'm sorry,
Like
what
the
is the
node?
argument we want to pass to myinit? I guess is the better way to phrase that.
Yeah, what do we want to put in the parentheses here?
Yeah.
Or... No, I don't know.
Is it the segment?
So not the segment, but what's the RxD sort of analog to the segment?
Oh, the node.
Yeah, the node. Thanks. So yeah, we can just call it node. And then we want to have like a conditional statement. So, and we want to compute the distance. So, does anybody know what the form of the conditional statement we would want to use would be? Anybody have any ideas? Or at least just generally speaking. So we know we want the IP3 to be 1 millimole between 40 and 60 millimole. Between 40 and 60 microns, right? So how would you sort of type that out as a conditional? Don't worry about the syntax about finding the distance, though.
So it'd be like if the distance or the length of the node is greater than 40 and less than 60.
Yeah, right. And actually, so Python lets us do, this sort of convenient, like between syntax. So yeah, between 40 and 60. And then the two things that we want to compute the distance between are the node and since we're using these terms like, from 40 to 60, we just want from the beginning of the dendrite. So does anybody know how you can compute the initial segment of the dendrite? Or not compute it, but refer to it? So this would be yesterday
Yeah.
from like segments,
Den bracket 0.
Yeah, right. Thanks. Excellent. So if we satisfy that conditional statement, we want to I think just return a 1. Yeah, 1 millimole. So,
and then what's the code for millimole?
Although, really, that's correct. Although, he doesn't have it in.
We didn't even import it. Yeah.
Millimoles is the default anyway, so that's our. We'll leave that as just return 1. And then what do we want to do otherwise?
Else return 0.
Yep. Excellent. All right. So
0 need a unit? 0 millivolts, 0 milli.
So millimoles is the default for this, but we could actually try, Joe, if you want to go back up and try importing millimoles from units. We can, do our due diligence and specify the units as well.
Cool. Here we can do.
So return 1 times millimoles.
Yeah, I guess that was necessary, because otherwise, how the software knows that you're talking about millimoles and not microvolts or whatever
It's
as
got a
Michael
default.
said.
Yeah, well, so millimoles is the default for RxD concentrations, but you're right, for like readability, this is much nicer.
But here, where is the concentration? I mean, you're just initialize a node, and you're just saying that if the distance is between something, just return another thing.
Right. So what we're going to do is pass this function handle to the initial value for when we create the species. So we'll see this in a second, hopefully. Actually, Joe, did you cut the region?
Oh yeah. Do you want me to put back into the bottom of this, or where?
Yeah, or if you want to make a new cell.
Might as well make a new
floats your
cell
boat.
for modularity. So a new code cell, and I'll paste that there.
Awesome. And then if you could
one thing I was noticing was that we're supposed to have a length of 100 microns up here. So we need to set our dend length up here.
Oh, right. Yeah. Forgot about that one.
And it's just called dend. So how do we just define the length?
Dot L.
Somebody already said it. .L.
Sorry, I couldn't hear it. I want it to be 100. That's good from there, right? So that's the 40 to 60 we put in, and then we'll add the region. Oh, an nseg. So we'll probably have to pick an nseg.
Oh yeah. Anybody want to suggest one?
Can we go with 30?
Sure. Well, we want to keep it odd, so let's say 31.
31, yeah.
Cool.
Shoot. So Robert has mentioned making sure that the nseg is divisible by 3. Is that, or like, can it be divisible by 3 or?
Oh, that's right. Yeah,
Odd?
Bill had mentioned that. So what's a number that is odd and divisible by
33.
33 works. Yep.
3. I forget. Why is it supposed to be divisible by 3? I hadn't heard that.
It's so that you have a segment that's exactly 0.5. I think that might be more Bill's.
Exactly 0.5. Okay, I got it.
Yeah. Okay, killer. Because that's something actually worth noting. If you have like a segment that's 0.33 and 0.5 and I'm sorry, 0.25, 0.5, 0.75. If you did 0.8, Neuron knows that you're talking about the segment at 0.75. It picks the compartment that you're in accordingly. But okay, so you now have dendar, and we need to specify IP3 as a species. So I don't know, Joey, you want to just maybe below dendar, or so we'll call it IP3 equals RxD dot species.
plus.
Okay, and then the first thing that we pass it is the regions, and that'll be a list that just has dendar in it.
List the dendar.
Yep. And no charge. Oh, we want D equals to 1.
Right here. D equals
lowercase d. We want to name it IP3. So just a string called IP3.
String.
And then for the initial value, we want to pass that the reference to that function myinit. So
and that's not a string. It's just the
it's just
function.
the function itself. Okay, awesome. So we've got that, and so yeah, if you want to run those, and then let's see if the plot comes out looking something like what Robert has.
All right.
Very nice. So I think Robert probably had a higher number of nseg. Well, I know he did, but you can see that ours is a little bit more choppy, a little bit less fine-grained than his was.
Yeah, let's bump it up to. So I would have, because there's 100 microns of length, I would have gone 101 here. Let's just see what that does real quick. I don't know if we can just replay it like this, but now it's much smoother.
Cool. And would you mind scrolling down a bit?
Yeah.
Cool. So find the time at which position 70 microns exceeds 100 nanomolar rather. What is the peak value obtained at that location?
So position 70 here, and 50, 100, 150.
Sorry?
Oh, I'm just kind of getting a guesstimate here. All right.
Oh, yeah.
Okay, so how are we going to go about this, Craig?
Well, does anybody have any suggestions? Yeah.
I'm running it parallel to you guys, and I'm getting an error when I was changing the nseg. Could I put it in chat? And
yeah, let me.
Yeah, sure.
Running.
Defined on a region.
The same here.
Oh, in the chat.
Yeah, I got that too.
Okay, does one of you guys maybe want to share your screen so we can see the whole list of the code? Because I can't put
yeah, I can do that.
Great.
And I'll be right back.
Okie doke. Okay, and so
I got that error, but I was still able to generate the graph, the plot.
I got this plot.
Oh, do you maybe want to try going up to runtime and then you can? Oh no. If you go to runtime and then do restart runtime. And then just run it from the beginning. So starting with the pip install. Okay. So my init.
Okay.
Okay, cool. So yeah, that's like an unfortunate thing. So when you run all these RxD functions and modules, it'll it's all like based on weak references. So like even though you've gone and overwritten that variable in Python, there's still some other version of IP3 that you've already made somewhere down in the ether. So yeah, for this, you just have to restart, run it again, start from scratch. So
really, anytime we're adjusting something, we should really run it all from scratch. When I'm coding, and I make a mistake, I don't go back one step and start there. I go back to the beginning to make sure that everything flows properly. But we're taking shortcuts in the class here.
Cool. So and that fixes everybody's problem, right? A couple of you added this error. Okay. Cool.
Yeah.
Sorry.
All right. So I'm going to share my screen again here. And it's the neuron diffusion exercise. Okay. So we want to find the time at position 70 microns exceeds 100 nanomolars.
You're muted, correct?
Appreciate it. I hope nobody's really like offended by my like blasphemy and cursing or anything like that. Okay, so let's set up a couple vectors to record this then. So does anybody know how we're going to record time? If it's easier to write it in the chat than it is to say it in English, that'd be good too.
Is it h dot vector?
Good.
Yep.
And then I know it's like, don't you do like the _ref _t?
Yeah, well, so
first though.
Yeah,
What
first
is the action you want to do to the vector?
Oh, record.
Yeah.
Yeah. And it's going to be, h dot
Now it's the
underscore ref t.
H dot underscore ref underscore t. Okay.
Okay, cool. And now we also want to record the concentration at 70 microns along the dendrite. Anybody know how we would go about that? So it's going to start off the same, where it'll be at h dot vector dot record. But does anybody know how we can access the concentration of a species at a particular place?
Let's see. Well, what is the species we want to do called? Yeah, here we go.
So you guys might remember from Robert's lecture, each of the species has a node list, right? So we can start off with IP3.nodes, and then you can actually get the appropriate node by passing IP3.nodes the segment that you want, that you're interested in. So how would we? So what would the segment be to record at 70 microns along the dendrite? Especially if, for instance, dend parentheses 0.5, if that's 50 microns along the dendrite, what would be 70? So remember, all this stuff is scaled to 1.
Is it 0.7?
Yeah, right. So,
yeah, it's 100 microns long, so 70% of it will get us at 70 microns.
Awesome, and then last we need to reference the concentration. So, Joe, there's more to that line.
Oh, sorry.
I know. So we got nodes passing that dend. Okay, and then so does anybody offhand know how you reference the concentration of the node? I don't know if Robert covered this, but it's going to be underscore ref underscore concentration. Oh, hi.
How you doing today?
Good, yourself?
Yeah, here's something there today.
Yeah, I'm actually in the middle of a meeting trying to. Yeah, sorry, no. I'm in the middle of a meeting. It's all right. Okay, awesome. So those, yeah, that's good. And so I guess we can run that, and maybe we can like plot it and see. Have a good one. see where it breaks whatever this value is, 100 nanomoles.
All right, how are we going to run it?
Initialize.
That was F initialize?
Yep.
Yeah.
And
Can do minus 65.
65. And we got the units, right?
Microvolts.
Anything else we need to do?
And then just H dot continue run. I suppose that was more of a question for the students, but either way. And let's we'll just do the same thing we did up top, where we did 150 milliseconds.
50 milliseconds. All right, shift enter. 0. Okay.
Okay.
Oh yeah, so it didn't seem to crash. Good.
And
so now we got. Oh yeah, let's just plot that real quick.
Yeah.
I keep getting in there.
Yeah, talk to Craig about it while I plot.
Yeah, what's up? Or Jessica, do you want to maybe post?
Oh, yeah, I didn't realize that I was whining with my microphone on. Sorry. Sorry. So I'm not even supposed to ask questions. I need to suffer through this. I just got an error in F initialize. Maybe I can't spell. I don't know. I've been getting errors throughout. I'm not used to working in notebooks, but it shouldn't matter. Oh no, there it is. F initialize. It's still giving me an error there, and it's not bringing me to anything that's useful.
Okay. Do you want to copy the error into the chat?
Sure. Oh, chat. Let's not Slack chat. Okay. Ooh, it's so ugly.
I don't know. Did you close your parentheses before calling h.f initialize? I feel like that's usually what happens when you get a syntax error on a new value line.
Yeah.
Is that it?
I think so.
Cool.
Nope. Nope.
No.
No, that line isn't happy. Oh, wait. I left a giant space here. What am I doing? Oh, no, it's still giving me an error. I lose today. Okay. Oh, I know what it is. Before ref, is that double underscore or single underscore?
Single.
Okay. For some reason, I keep doing the. Oh, I don't think that was it though. I have this bad habit of doing the double underscore. Okay, let's see. This should work this time. Doesn't like that line. Here, I'll copy paste it again. But don't spend too much on me. It's okay.
Yeah.
I mean, I have.
Unless everybody else is having the same problem, we should probably keep going.
Yeah, there's something. Sorry, I will keep my microphone off so I don't complain. Sorry, guys.
Fair enough.
All right, so we got a nice plot here. What do we do next?
Okay. So find the time at which it exceeds 100 nanomoles, and what is the peak value obtained at that location? Well, I mean, we can just look at the graph, right? It peaks at 0.25. I mean, even though, yeah, I think we have to import a. Oh, that's right. Max is just a built-in function. And then what time does it exceed 45? So anybody have a suggestion for how we would figure out where it exceeds that value? I would use NumPy, but I don't know. Maybe somebody has a simpler solution.
Yeah, I would have used NumPy. I would have used the argmax function of NumPy to find the maximum in the concentration, and then just use that as the index for the time.
I like it.
Well, so actually, there's an argmax. Yeah, there we go. Although, but we don't want the maximum. We want it where it's above. In this,
yeah, that's true.
0.1. So what we could do is consider time and cons. Yeah, right. So Hector's got the right idea. So we could use. Actually, what would be the syntax for this? It would be like np.argware.
What do you think I'm doing here?
Oh, do you actually, Hator, do you need to use the 2 Python? Or I think conc should be something usable.
I'm not sure it have to use, but works very well. I don't know what happened if you don't.
Okay.
So yeah, I think if we just, I'm just gonna brute force it. I'm gonna go through every time and every concentration, and as soon as it hits 100, print out the time. I guess. Yeah.
Yeah.
If you do conc greater than 100, it returns the vector where it's false, where it's not greater than 100, and
oh, that's interesting.
It's greater than 100.
Okay. And then you need to have an extra statement for the.
Yeah. So if you want to tell me how to type that out, I'm happy to. Let's try that.
Sorry. So the concentration. Wait. So exactly what are we finding again? Where the
we want to find the time when our concentration, which is at 70, hits above 100. So I want to find the concentration. Oh no, the concentration hits what?
Yeah, the concentration
100 nanomolar. What's that? 0.1 then?
Yeah.
So it'd just be conc greater than 0.1.
Okay.
And then you can get the times of. You could save that to a vector.
I'm not quite sure how to do this. Somebody typing this into chat to give me a. Yeah, greater than 100. Oh, just that. Okay.
Oh, well, we wouldn't want to use 100 because the values are in.
Oh, yeah.
Right, so we would want 0.1. But.
Concentration is a list, yeah.
Yeah, so we wouldn't want to do quite that.
I think we could do like what do they call this? What's comprehension? Concentration. Yeah, I'm not sure how to do it this way. I'm going to work on my brute force way while you guys think about it.
Yeah. Okay, yeah. So if we made conc Python array, or wait, this is so inconvenient that I can't actually run the friggin' exercise myself. But, oh, now it's starting to work. Now I can run things.
Printing every time after that, so this is not a very efficient way to do it.
That does it.
Well, you want to, Joe. I think you want to put them in a list, and then it's just whatever the first element of the list. Actually, yeah. You could make a.
Yeah, it's the first element of this list. Oops.
Yeah.
We'll have to scroll away.
Also, in the chat, this works too.
In the chat.
Okay, right on.
Next.
Okay, I think we all understand that there's multiple solutions to this problem, and
many ways to do this.
We're all just kind of cool.
It's at
all right, so I'm sure we don't have time to do both of the other exercises. Do you guys want to choose which one to do next? One is an implementation of the Hodgkin-Huxley channels with RxD, and that's kind of cool. We get to see sort of where straight neuron kind of is unrealistic, where we can be a little more realistic if we use RxD, or the other one's this regenerative signal thing. Any firm opinions, votes? People not care?
First one, Claire says.
Okay.
So that was the Hodgkin-Huxley one?
Okay.
Tab. Watch Huxley example. Share. All right, HH example 2. This is the one.
Yep. Okay, so I think a lot of this is sort of worked out already.
Okay, so import H, import units, load the standard run, import bouquet and bouquet plotting. And then we
Okay, so basically, like, just to run you through what is already in the notebook, right? So we have just, we have our axon, nothing else attached to it. We had a current clamp to the middle of the axon. We have the current clamp that lasts for, what is this, 100 seconds. We record the voltage and the time. We run for 200 milliseconds. And then we get lots of spikes, right? Everybody sees that? Or, well, we'll let Joe finish running through it, and then we'll see many beautiful spikes. Oh, no, a single spike. What?
How long are we running it for? What is this?
Well, and what's the duration of... Oh, he's got only the single spike. Okay.
And yeah, it only ran for 10 milliseconds.
Okie doke.
Yeah.
Oh, all right. Okay, well, so the exercise is then to make it fire periodically. So what can we do, namely to the current clamp, to make it fire, at a constant rate, or at least, more or less constant?
Would you increase the duration of the current?
Yeah. You can see if you go down to exercise 3, he says that, T approaches infinity. So let's do it for like 5 seconds, I guess.
Yeah, so what did we want to
So
do?
if you could actually just, on that cell below, just, change the dir.
So what do we want it to be?
To like 5,000 milliseconds. I was going to say, well, you could leave that cell as it is.
Oh, okay.
And just, copy.
Z. Oh, shit.
Oh, no.
Control MZ. What? Okay. Is there an edit undo?
Wow.
Okay, well, I lost.
Here, I'll copy it into the chat.
Okay. There we go. I see. Paste. Okay. And then you're saying just do it below here?
Yeah. So you could just do ic.dir. No need to remake the iClamp.
All right. So 5,000, 5 seconds?
Yeah.
Okay.
But you can delete that ic equals h.iClamp because we already put one there.
Whoops. Okay. Oh shoot! Is that going to create another one?
I don't really know.
It's running.
It might. Not the end of the world, but either way. Okay, so yeah, let's just have a look and we also need to run the simulation for longer as well. So we might as well make h.tstop something big, another 5 seconds as well.
We do milliseconds on that as well, or does it matter there?
That doesn't matter. Again, milliseconds is the default, right? So,
What is h.tstop?
well, so until now we've been using h.continue run,
right,
where you pass it the value that you want it to go to. There's also h.run, which sort of packages h.continue run into it, and uses this variable h.tstop as the place it wants to stop at. So, So yeah, and then Joe, if you want to like reinitialize and
restart everything.
Yeah, I didn't mean like the whole thing. I mean reinitialize the H
okay.
initialize.
Functions. And what do we do? -65.
Sure. And then I guess we can just use h.run here since now we have different h.tstop. And then if you want to copy the plotting down there too.
Yeah, so the recording should already be set up. I just need to plot it again. Is that right?
Yeah, yeah.
All right. So I got to run this one, shift enter. Shift enter.
Oh, okay. So
only went to 5 milliseconds.
Oh, did you run that cell that you're? Oh yeah, you did. Maybe just try h.continue run rather than h.run, and pass it 5,000.
Oh, here we go. 5,000. Now we got it. I don't think I entered the cell where I put the T stop.
Yeah. But we only get this one spike. So
well, this is probably a bunch of spikes. This is 5 seconds we're looking at.
Yeah, right. But we do want it to keep spiking the whole time.
Yeah.
So maybe we can. Well, anybody have a suggestion for how we can keep it spiking the whole time, or?
Sorry, what did you change to make it from 5 to 5,000?
This h.t stop.
I see. Okay.
Okay, so if we do it for 500 milliseconds, we really spiking. We're getting some depolarization blockade, it looks like.
Yeah. So anybody have a suggestion for how we can get rid of or work around the
increase
I believe the amplitude of the stimulus is too high.
Yeah, right. So let's try like an order of magnitude lower.
Yeah, we'll do that.
Cool.
Ah, that looks better.
Awesome. All right. So that's exercise 1. Exercise 2 is we want to see what the intracellular sodium and potassium are or verify that they're constant. So anybody want to tell us how to record intracellular sodium and potassium?
So we're going to have to record it, right?
Yeah, probably create a h.vector and record section dot underscore ref underscore something.
What's our section called?
Yeah, our section's axon.
Axon, okay.
Yeah. And yeah, we're stimulating in the middle, so it's record in the middle.
All right.
And then, yeah, ref underscore NAI.
I think it's NAI, yeah.
Yeah, and then, and actually, I'm not sure if that'll like violate the namespace. You want to maybe name the.
Oh yeah, good call.
The vector like NAI vec or something like that. Yeah, my NAI, that works too. Cool. And then, yeah, same thing for K, and we'll plot those.
KI.
Yeah.
Underscore ref underscore KI.
Yep.
Okay. So that'll get our vectors.
Cool. And then how are we going to go about plotting them? Anybody want to chime in?
I mean, we can just do the matplotlib, the same thing I did before.
Well, we have to rerun the simulation, though, right?
Oh, yeah, good point. Sorry.
So we'll reinitialize, rerun, plot again.
And then H dot. Have to run now.
Yeah, we can use run now.
And that should be good. Okay, and now, yeah, let's add another code cell. Did we save time? We did, didn't we? Yeah. Time versus
my NAI.
Oh, yeah, my NAI, thank you.
Oh, you need an I at the end of that.
Oh, I've got the bouquet plotting instead of.
Oh, yeah. I also.
Oops, let's see here. And yeah, I'm not that familiar with the bouquet plotting, so I'm just going to import matplotlib.
Yeah, me neither.
Plot is PLT, and then plot. Time is not defined.
No, we called it T.
Oh, T, thank you.
But you also need my KI. You just got my K right now.
Yep. Yeah, okay.
But also one more instance of time.
Oh, thank you.
All right.
There we go.
Looking super constant.
Looks very, very constant.
All right. So then the next exercise is that we're going to define sodium and potassium as species. So what do we have to do before we define the species in RxD? Before you can have chemicals, the chemicals have to live somewhere, right?
Do you have to define a region?
Yeah, cool. So let's just call it the site for cytosol. That's usually the convention. And then it'll be RxD.region.
I think it needs to be imported. I didn't see.
Oh, we haven't imported RxD yet. Okay.
Thank you.
Good call.
Is that from Neuron, right?
Yep. And we'll do the sex equals H dot all sec.
Say again.
Sex, like SECS equals H dot all sec. Lowercase s. Open and close parentheses. Awesome. And then the next argument is going to be NRN underscore region or regions, plural, I'm not sure. And that's going to be equal to I as a string.
And there's no S.
Okay, thanks.
Region.
Thank you.
And last thing is a name, so just call it site.
String, yeah.
But I do think you need the keyword name.
Name equals.
All right, girl. And now we can declare Na and potassium. So anybody want to walk us through the syntax for that?
A region.
So is it RxD dot species?
Mm-hmm.
Yeah, what do we want to call it?
Well, we should call it Na.
Okay.
NK.
Okay.
Might as well.
Okay. So Na equals RxD dot species.
And the first thing is going to be the regions, which is just site. Actually, I lied. You don't need to have it in a list. That's a NetPyNE rule. We'll name it NA. And this is actually important. Who knows the charge of sodium?
One plus.
Good. Positive
right.
one.
Positive one. And then we'll do the same thing for potassium. So we'll call it K. We'll name it K. It'll live in the cytosol. And it's going to have a charge of 1 as well.
So name equals K. Charge equals 1. Okay.
And then, Joe, if you could just reinitialize and run and then plot all the good things that we plotted before. See if anything's different. And does anybody have a prediction for what might be different? So, like, we talked about, or, Robert talked about how in the, squid giant axon, if you're using Hodgkin-Huxley equations, the concentrations don't really matter all that much because the number of ions is so small. But does anybody have any predictions for what will happen when we do start to keep track of intracellular potassium and
that's the
sodium?
Okay, so these are the runs. So I'm going to do a new.
Well, we'll see the concentrations move. I believe it's sodium goes into the cell more as the cell fires, and potassium will leave the cell more.
Yes, right. So sodium will continue increasing, potassium will continue decreasing. And then what about to the voltage trace? Oh, actually, Joe, you want to plot it even longer than that? Or like run it even longer than that?
Yeah, sure. I can H dot T stop.
Yeah.
Shouldn't it eventually reach an equilibrium? After you lose the.
Well, it would, but we're continually applying a current to the cell, right? So we're driving it to keep it spiking. And I guess but I guess it'll reach an equilibrium like that. Yeah. So wait, what did you set T stop to be?
Oh, it's equals. You don't call it as a function.
Oh, right.
We want it 5,000?
Sure. All right, cool. So, and yeah, you do actually see it, or voltage reaches like this sort of plateau equilibrium value. Way out there at 5,000.
Yeah, let's also plot the concentrations, huh?
Yeah, that'd be great.
Do you not have to reset like the record vector with each continued run or each instance?
Wait, are you asking, do you have to reset them?
Yeah, or is it just like once you initialize the record vector, it's like always there and it'll just kind of adapt to the new run?
Yeah, so the latter. And that's because, to create the record vectors, you're like passing the reference to the value that you're trying to record. So as long as that doesn't change, the vector will keep recording whatever it is that you do. What is important, though, is if you are going to do like multiple runs, your vectors are going to get overwritten.
Mm-hmm. Oh, okay.
Yeah, so I didn't.
Yeah, you can't actually plot them like that. So you could record it at a place like we did in the last exercise.
Oh, okay.
Test of your, recollection, Joe, or you could just actually plot the vectors that we already pointed to earlier, which are like my NAI and
there we go. Yeah.
KI.
There we go.
Excellent. Cool. And so this is the kind of thing that actually ends up happening in like pathological brain states, like cortical spreading depression, or following like an ischemic stroke. And it's not a good thing. Or if you were an experimentalist, you probably would have killed your cell by now, right? Exercise 4 is how can we have a homeostatic phenomenological model to get the initial behavior back? How does that compare to a sodium-potassium exchanger? So how can we try and rectify this imbalance? Get some of the sodium back out, put some of the potassium back in, or the other way around. Right, yeah.
Some leak channels?
Yeah, we could do a leak channel. That's a good idea. And you know how we would specify that with like a reaction diffusion like framework. Well, okay. So there's a couple things we could do. We could just have a rate. So an RxD.rate where we just take out a constant amount of sodium, or we could have the amount of leak be proportional to, or not proportional, but the amount of leak could be based on some sort of like driving force, like a, like a reversal potential type thing. So rate's going to be, oh yeah, that is capital. So the first thing for the first argument to rate is going to be the species that we are going to change with this thing. So start off with sodium, and then we need an equation for the rate. So anybody want to specify an equation or just even a constant value to leak it by, or to leak it out?
So it should involve the concentration of sodium, because the higher the concentration, the faster it's gonna leak. But it is we got the next session starting at 3:30.
Oh, okay.
So I'm not really sure we have time to get through this, but we could play around with it at the end of the day during the working around stuff.
During what?
Network in Neuron. Oh, there's hands-on exercises from 5 to 7. Yeah, coming up at 3:30 is Neuron and Synapse Theory. Network and Synapse Theory.
I think the exercises from 5 to 7 are for the networks.
Okay, so it's already scheduled for that.
So I'm not sure how far along Robert has gone.
Okay.
I think it's also an example too. Maybe if you guys want like maybe 10-15 minutes more, and we can delay everything a bit back.
That works for me. Then we can do this this last exercise here. And
sure.
Yeah, sure.
Okay, so we need an equation for the sodium, yeah?
So I think one place we can start at is like, so what's the initial value of sodium, or the initial concentration for intracellular sodium? So we can try and drive it back to the initial value.
Oh, yeah.
Is that 10 there?
Yeah, right. So how would we set this equation up if we wanted to constantly push sodium back to 10?
Something related to the difference between the actual concentration and the 10.
Yeah, right.
Sure.
The difference.
Yeah, you could do 10 minus the concentration of sodium. And then, we can either multiply or divide that by some sort of factor. We can just leave it as is for right now and then play around with that.
Yeah, we can try it right now. This is right now. Anytime it's different from 10, this leak will drive it back to 10, right?
Yeah. And then we want to do the same thing for the potassium, right? So what's the potassium initial value? Just approximately anyway.
Approximately 55.
55. Cool. All right, and then let's reinitialize and see what pops out.
H dot, yeah, T stop should be fine. Then just H dot run.
Yep.
It's initialized to positive 65 millivolts. Should it be negative? 65?
Oh, thank you. Yeah, that'll be problematic. Freaking neuron out. And then, yeah, we just want to plot T and V. Plot dot.
Oh, good.
Yeah, the restored it.
Yeah. Actually, that did it pretty well.
Yeah.
So maybe we don't need to bother with factor.
Out of curiosity, would driving it with hill function work here as well?
I'm sorry, could you say that again?
Yeah, would driving the Na concentration towards the value we want would work with the hill function in this case?
I don't even
Or is it
remember
something
what
that's
the
not-
hill function is. Jesus, what is the
With the cooperativity and such, because I've seen he talked about it a little bit in the lesson.
Oh, yeah. And actually, I mean, so that would probably be closer to the real sodium potassium exchanger, right? So the way we have these two leaks right now is fairly unrealistic and not actually what happens in real cells. But does anybody know how a sodium potassium exchanger works? I think it's like it requires ATP.
What?
Oh, sorry, go ahead.
Isn't it an ATPase that trades them?
Yeah, right. And it also trades them unevenly.
Two for one or something, right?
I think it's 3 for 2, maybe.
3 for 2.
But either way, yeah. So yeah, we could definitely incorporate some more complicated dynamics to get a more realistic.
One thing I'm just going to try real quickly is usually you've got a time constant to because right now the change is instantaneous. As soon as there's a difference, it instantaneously starts adjusting. I'm going to add a little time constant just to see what this does. It might not do that much.
You're gonna. I played around with it. You're gonna want like 1,000.
Oh, okay.
Then it's kind of interesting.
Oh yeah, it's like being shorter spikes or not as tall. Yeah, interesting.
Cool.
So with the time constant much slower, the spiking is it's not the time constant's not fast enough. The rate's not fast enough to replace what's happening in the spiking. Yeah, cool.
So, I mean, we definitely don't have enough time, I think, to go through the regenerative signaling example.
Yeah, I don't think so.
I mean, if any of you guys want to have a look at that in your own free time and you have questions about it, you can definitely ask me or Robert, for that matter. Or I'll volunteer Joe too, but
but I know less.
What is regenerative signaling?
So, I gotta be honest. The example is like sort of just is sort of arbitrary and doesn't really use real ions or anything. It's just kind of a dynamical systems thing. But I honestly don't even have a good definition. Well, I guess it would just be a like a repeating signal of some kind, right?
Okay. Yeah. Okay. That makes sense.
Yeah. So like, if you look at the example, he's got this sort of, equation for the change in some arbitrary value y as a function of time. And it's part of the equation is the diffusion equation that we saw earlier, and the other one is this function of k and the value of y, and this other parameter, and this will let you get periodic sort of fluctuations in y.
Okay.
Thanks for showing that.
Cool.
All right, if there's no more questions, let's take a quick break before the next session, huh?
Yeah, sounds good. All right, thanks, guys.
Okay, thank you very much.
Thank you.
When is the
Thank
next
you.
session?
Here, I'll check real quick.
Sorry.
And Salva, you can go ahead and quit recording.
The next session is at 3:30, but did Salvador say we'd push it back on the 10 minutes? Or
I'm looking on Slack right now to see.
Okay, yeah, I can look too. I appreciate it.
Yeah.
Sure.
Just if you had it available.
Should we go back to the big meeting?
Yeah, I think so.
Oh yeah, let's do that. We'll see you guys.
All right, adios.